Alright, what is going on, guys? It is Brickgeneral here, and today, guys, I'll be teaching you guys calculus through Minecraft. So, in calculus, after learning about limits and derivatives, you can learn about integrals, also known as antiderivatives. When you define the bounds of an integral, called a definite integral, is essentially taking the area under the curve. So right here, I've built this absolutely lovely curve. I know, I'm quite the artist, you don't have to let me know. But I built this in Minecraft, so obviously I'm restricted by the fact that you can only use blocks in this game, but it should get the job done for what I'm going to show you. Obviously, the most intuitive way and most precise way to calculate the area under it would be through an integral. But if you have no previous calculus experience, you can use rectangles. So the way we do this is we build rectangles under the curve. Now, right now, I'm going to start with building kind of big rectangles that have very large lengths, and what this does is you can kind of estimate the area. So you could take like the length of this, so this is about 6 blocks, so you could take that as the length and the height, which is 3 blocks over here, and then you could stretch this over this area. So right here, because we're defined by blocks, this would actually give you pretty close to the definite area right here. And then what you do is you just keep going up until you get to the height of the curve, and you just keep making rectangles like this. Now, this strategy won't give you the exact area under the curve, but if you keep making smaller and smaller rectangles, you can get infinitely close to the actual area. So right here, I've done basically just arbitrary lengths of the rectangles, but they are very large for considering that 1 block is the lowest you can go. So right here, guys, this is actually pretty close to the actual area that'd be under here. But once you get over here, you can start seeing there's a lot of discrepancies here that are not accounted for with the rectangles. So what this is doing is this is actually a gross underestimate of the entire curve. You can see all this is not accounted for, and all of this up here is not accounted for. As you can see, because the height is constantly changing and we're only accounting for the height at a specific position. However, if we switch this to rectangles of just 1 block that just have 1 block width, that would be a lot more accurate. Now here in Minecraft, when you use 1 block width, basically rectangles, this is going to be exactly the area under the curve. As you can see, there's nothing wrong here. This is completely right. However, obviously in real life, there's no smallest value. There's no like 1 block that you can go automatically the minimum to. You can't just make the width of the rectangle like 1, and then that'd be exactly it. Because obviously there's going to be discrepancies that you can't account for in an equation that's not linear. So if you have something like this, obviously it works out here, but if you were to do this in real life, you can't basically just keep making it smaller. You can't do like, oh, I'll do 0.1. That's still not going to get you the exact value. Of course, if you keep going smaller until you get like infinitely close to 0, you're going to get basically as close as you can to the actual area. Now the reason this works is obviously it's going to be accounting for the exact length under the curve every single time. So in a real curve, or if I were just to demonstrate this in Minecraft terms, and this were basically moving through the block like this, and your smallest value was only 1 block, you wouldn't be accounting for the stuff that'd be moving up through here, and that would still leave a small discrepancy. If you moved it down to 0.1 blocks instead of 1 block, it would be a lot more accurate because you could account for that, and if you just keep making it smaller, you could account for that even more. Then you calculate the area of all the rectangles, add them together, and you basically get an estimate for what the area is under the curve. This process of creating rectangles that are under a curve to estimate the area is called a Riemann sum. And that's basically the basics of it, just taking rectangles. Now I'm going to hand it off to Srihan to talk about left hand, right hand, midpoint, and all the fun stuff about a little bit more advanced Riemann sums.
Hey guys, it's Srihan here, and I'm here to talk to you guys about left, right, midpoint Riemann sums, and additionally trapezoidal rules, or also known as the trapezoidal rule. And so something to note is that these graphs are actually going to be bigger than Nij's. I could never live up to Nij's artistic ability, but I'm allowed to use commands because I'm on PC. So that's just something to keep in mind, and I hope you enjoy our amazing project. So just as a quick recap, when n, or the amount of rectangles, equals 4, the area under the curve that is not accounted for is larger than if the amount of rectangles is higher, because when you have more rectangles, each point is closer to the curve. Therefore, as the amount of rectangles goes to infinity, or n goes to infinity, you get closer and closer to the area under the curve. Alright guys, so here are 2 of the basic Riemann sums that we're going to learn. As you can see, both of these graphs are increasing, and the ones that have rectangles starting on the left endpoints are left Riemann sums, and also the ones starting on the right endpoints are right Riemann sums. So basically, what you want to note here is that on an increasing graph, the left Riemann sum from a to b will always be less than the actual integral from a to b of that respective graph. And on a right Riemann sum, you can see that the area of that Riemann sum is actually going to be greater on an increasing graph than the integral from a to b on that graph. Also, something we want to note here is if we just flip these graphs around, ignore that, if we just flip these graphs around and look at this, you can now see that these graphs are decreasing. And you can see with the right Riemann sum, it's actually less than the area from A to B. And this is because on a decreasing graph, right Riemann sums will always be less than the actual area. And on a decreasing graph, left Riemann sum, they'll always be greater than that area. So this is just something you want to note and remember, because these rules apply to pretty much every single graph. And so having these just memorized is really important. Additionally, in order to calculate the area of each of these Riemann sums, you just take the width of each rectangle and multiply it by the height. The width is also known as delta x. And so basically, you just multiply the width by the height, the normal area of a rectangle, and then add each rectangle. And then as you can see, it gets us the area of this light blue area. So that is how you find out the area of each Riemann sum. Alright guys, here are two more accurate methods in finding the area under the curve. Now, these methods aren't going to be more accurate than a definite integral, because a definite integral gives you the actual number. However, these will be, at most times, more accurate than the left Riemann sum and the right Riemann sum. Now, on the left here, we have the trapezoidal rule, which is just as it sounds. There are multiple numbers of trapezoids, and basically you just find the area of each trapezoid and add them together. And in this case, it would be the length of A plus the length of B. Divide that by 2 and multiply by the height of each trapezoid. And adding these together will give you a really close estimate under the curve. But as you can see, there are some discrepancies that are not accounted for, but this will give you a close estimate. On the right here, we have the midpoint Riemann sum, which is sort of like the left Riemann sum and the right Riemann sum combined. Instead of using left endpoints or right endpoints, we use midpoints. So by using midpoints, the area over the curve is supposed to account for the area under the curve. And we can see that although it does do that, it's not 100% perfect. So you can see that the area under the curve might be a little bit bigger than the area over the curve, or vice versa. So that's just something you want to keep in mind about the midpoint rule too, that neither of these methods will give you the exact value. However, these methods will give you a really close estimate. So finding these areas is just like the rectangle. You just find the area of a rectangle and then add them together. And that is the trapezoidal rule and the midpoint rule.
Alright guys, that is the end of our project. Hope you guys enjoyed. Don't forget to leave a like, comment, and subscribe. If you guys think we deserve 100 or an A+, let me know in the comments below. Catch you guys in the next one. Peace.